Hello, everyone. This is Roger Schmitz with Moxy. Welcome to the Swiss Professional Hockey Training webinar. I'd like to welcome all of our attendees that are joining us. It looks like we've got about 12 or maybe 15 online right now. A few more are just coming in. This is the second in a series of webinars that we're doing for public consumption on Moxy information. If you want to take a look at the first webinar that's been recorded, that's posted on the moxymonitor.com website. If you go into the training tab, there'll be a section on webinars, and you can sign up for future webinars in that space, as well as review past webinars. Our presenter today is Andrew Feldman with Swinco Performance Labs out of Zurich, Switzerland. Swinco is a training consultant, and they work with all kinds of professional athletes, hockey players, figure skaters, downhill skiers. They kind of run the gamut there. Andrew has a master's in exercise science, and his master's degree specialized in near-infrared spectroscopy. So we're really lucky to have him today as a presenter. So with that, I'm going to turn things over to Andrew, and he can dive into the presentation.
All right, thanks a lot, Roger. So what I want to do today is actually tell more of a story, how I and the people I work with introduced NIRS and the technology of Moxy into a new marketplace in Switzerland. So that's why I have a Summer of Hockey, which is a nice storybook title. Before I start, I have to give credit where credit's due. So I want to thank Elite Training. They're the conditioning coaches that I work with that train the Zurich Lions. The Zurich Lions are a professional hockey team in Switzerland that we do consulting work for. They're also one of the top teams in Switzerland. And then I also want to thank Brian Kozak from Next Level. He's a hockey trainer from Canada that we work with quite a bit as well. That does a lot of live research work for us, so I need to say thanks to them. But now we can get started. So a little bit about myself quickly. Roger already mentioned I studied sports science and exercise physiology in Canada and in Switzerland. In Switzerland, I then started up a company to do training consulting, and we really focus on new and innovative technologies to try to better training capabilities. So in this story, I want to really introduce the trainers that I started working with for this ice hockey team and the road that we took to integrating new technology like Moxy into their training procedure to really try to optimize training for this ice hockey team. So we're going to go through 3 points. The first point is just the approach. So how I approached the trainers, how the trainers approached these new concepts, and then how they applied it. So how they applied it to performance assessments and how they applied it then to training. Generally, I won't be going too deep into physiological aspects, but there will be a chance for questions. If something goes unexplained, please just ask me. So the first point to really talk about is when I approach these conditioning coaches, I always kind of had an ace up my sleeve because I'm Canadian. So in Switzerland, everyone thinks you know lots about hockey. With that point of view, I said I'm an exercise physiologist and I'm from Canada. So they said, great, you know something about hockey. We want to work with you with this professional hockey team that we do conditioning for. And I talked to them about, well, what are the ideas? Well, what do you guys use? How do you guys use physiology in order to optimize training? And they really said, well, we don't really use any physiology because the only physiology feedback we get are from the clinics that do physiological testing for the ice hockey club. And these are two very separate things. So the training is very separated from the physiological assessments that the players do. And in this way, I really was able to introduce new technologies and say, well, shouldn't these physiological assessments be much more coupled with the actual training that's going on? And that's where we really went through information and we tried to discuss options and possibilities that are available in a very theoretical way, could we not do a better job by integrating testing and assessments much closer to the sport and to the training itself, rather than having these two separate units? They were pretty quick to understand the opportunities that were available. One of the biggest questions they had, and what this is I get often from coaches, is, was everything that I was doing before wrong, or what was right? And my approach to this is always the same. When taking something new, you need to be open. You need to be willing to accept new things, but you can't just accept everything and change everything all at once. So I don't know if people are aware of Lawrence Krauss. He's a physicist in the US, and he always says, you have to keep an open mind, but not so open that your brains fall out. So the moral of the story is, we need to be innovative, but make sure we take everything a step at a time. The point being, really balance skepticism and innovation. Don't just, if something new comes, toss everything out and hop onto the newest trend. Really analyze what you're doing, what makes sense for you now, what may make sense for you in the future, and then baby step through the process. And that's really what I did with these conditioning coaches, in an attempt to really get them to learn what's happening, to understand what's happening, and then to choose for themselves, okay, this is really where I think it's going to be able to help the hockey players the most. And the final point on this slide here, never lose sight of the ultimate goal, is that physiology is great and interesting, but the goal of training isn't necessarily the physiology. It's the performance that understanding and applying physiological theory gets you. So performance is the goal of training, increasing performance, and I have health actually above performance, because I feel an athlete's health is also a major point to be addressed, because sometimes you sacrifice one for the other. So just that I also have said that. Now, we discussed this all in a very theory-based sense. What can we do? What options do we have open? How are we going to baby step through this? Then it really came down to, this is great. We really feel we have this new tool. We have new tools. We have new ideas. But from a practical point of view, what are we actually going to do now? It all sounds great, but how are we going to integrate it to help us? And from a physiological point of view, there's really two main aspects that we then discussed. The first one is performance assessments, performance testing, performance diagnostics, to look at an athlete's physiological abilities prior to training, during injury phases, and so forth. And the second one is, can we use these new ideas not just for the diagnostics, not just for one assessment or one test, but can it also help us actually during every training to optimize the time that we have? So I'm going to go through these 2 points and how we attempted to apply and try to make sense of the ideas that we used. And really the understanding is, what I'm going to present are the baby steps that we took with these conditioning coaches, who are really open, but will also want to ensure success. So they want to use ideas that they know work, and they want to integrate new ideas that they think can help. So the performance assessments and the trainings I will show are really the baby steps, and I feel there's a lot more that can be done, but the approach, again, is baby steps, integrating new ideas step at a time, what is successful, and continuing down that path. So when we talk about performance assessments, we need to compare and contrast at what else was available for ice hockey players and what else do ice hockey players do. So generally, an ice hockey player, this is also in the NHL, in Switzerland it's also the same, they do a lot of cycling-based tests. So you have some strength tests. They do max squats and deadlifts and so forth. And then they do a Wingate test, and they do a VO2 max test. And it's pretty easy to convince a hockey player and a hockey trainer, that this does not make a lot of sense, that cycling is not ice hockey. So that is actually a pretty easy sell. And once that was sold, they came, well, how can we use this new technology, Moxy in this case, to help to create an assessment that is going to further our training. So what do we need out of the assessment? Firstly, we don't want to make the same mistake as the other tests, so we don't want to just use it on a bike. We want it to be sport specific, which the Moxy is real nice because of the format that it's in. It allows you to be very sport specific. And the second point is we want it to be function specific. And what I mean by function specific is that an ice hockey player doesn't skate for 30 minutes at a medium intensity. A hockey player does high intensity followed by break, and high intensity followed by break, repeat, repeat. This is a very different type of stress on the body than a 30-minute or a 60-minute skate on an oval, for example. It's both skating, but the physiological demand is very different. So we want to make sure that the new assessments also encompass this. So we did basically a kind of like a sprint interval test, where we get them to do high intensity followed by rest and repeat. The question then was, okay, we think the assessment's good, we can get it done like this. What are the goals of the assessment? What should the assessment result in? And I actually feel this is one of the bigger problems with testing that's done. Is the goal of a physiological test to figure out what your maximum performance is? That could be one, so that you could document improvements. I think that is important. But what often goes lost is that the goal of a test or of an assessment should really be, how do I structure my training for this athlete in this sport? Which is why the need for it to be a sport-specific assessment is so high, because it's really about focusing on, in this case, hockey and not on cycling. This is actually also one of the biggest comments that I get from hockey trainers, that they get data back from the team's physiologists from a Wingate test or from a VO2 max test. And I ask the conditioning coaches, what do you do with that information? And they say, well, nothing. It's not usable in any of the training that we do with the athletes, which kind of shows the whole training guidance aspect of a test or an assessment is lost if the coach or the conditioning coach doesn't even look or use it. So that's a very high point on when we do an assessment. It needs to create something usable for the coach to help maximize improvement for the athlete. And I'm going to show some of the assessments that we did, some of the results, and try to explain what we see and how we try to rationalize different approaches to training based on those results. So what we have here, this looks like a lot, so I'm going to try to take us step by step. I'm actually going to try to zoom here a little bit to get this picture a little better. Hope that's zoomed there. So what you see is you have the green curves, that's the SMO2, and the brown is THB, so indirectly blood flow. And what you see here is 1 minute, so 60 seconds of rest, followed by 30 seconds of a maximum intensity skating, and then followed by a period of rest again. So what do we see when the intensity starts? You see that a lot of oxygen is being consumed right away to create energy for that intensity. The athlete actually bottoms out pretty close to zero, about halfway through, and then at 90 seconds there's the the activity stops, they sit down on the bench again like they would in a game, and you have a recovery curve of SMO2 back up. See if I can get out of that. There you go. So what we look at is exactly that. We look at what does SMO2 and total hemoglobin do during the 30-second intensity, and very, very important, and this is what often gets lost in other assessments, is what does it do after the intensity is over? How does that athlete recover the SMO2? And based on how those curves change, we identify 3 basic patterns. So this is based on experience and empirical data collection that we've done for quite a few years now, actually, with hockey, that we see these general patterns that are happening. And one is a utilization limitation. So what we mean there is the reason that their performance is not higher is because they somehow have an inability to maximize the oxygen that they're taking in, so to maximize the utilization of the oxygen. They're bringing in oxygen, but they can't use it sufficiently enough. We usually talk also about a muscular limitation when we say that. When we say just the muscular capacity to use the oxygen in an oxidative way does not match the ability to supply the oxygen. So I hope that makes sense, otherwise you can ask a question. A supply limitation, what we mean by supply limitation is basically the opposite of a utilization limitation. What we mean is the athlete is really good at using the oxygen that is being delivered to the point that he or she is not actually being able to supply enough, that they end up bottoming out on the oxygen availability in that sense. And the supply respiratory is a special case that we saw, and that is when we feel the reason that the supply is actually being limited, and this often has to do with recovery as well, is the respiratory system, which means the respiratory muscles are not adequately enough trained in comparison to the rest of the body to uptake oxygen, and very importantly also to eliminate CO2. I'm going to show 3 different pictures that each will show these different limitations so that we can see what we're looking for exactly and try to rationalize why we make those decisions. Based on which limitation an athlete is identified with, that then defines to a certain extent how parts of the training of that athlete may vary from a different athlete. This is where we get into how an assessment like this not only gives you a performance parameter that you can compare to after a summer training, but it also gives you information as to how exactly you should approach this summer training and why not every athlete should do the exact same thing potentially. So what I have up on the screen here are 3 different examples. It's the same protocol as I explained before. So you have a minute calibration break with a 30-second bout and then recovery. And you see these are 3 actual tests, and you see 3 different curves. And I'm going to explain the differences in the curves and the rationale that we had behind identifying them differently. So we're going to go with the 2 on the right side. One of them at the top is labeled utilization, meaning here we identify a utilization limitation, and the bottom one is supply, and we identify a supply limitation. So if you look at the top one, you see that yes, as soon as activity starts, the high intensity activity, SMO2 drops off nicely, and it drops off nicely for about 15 seconds and then kind of plateaus out for the last 10 seconds at about 30%. Now, it doesn't really matter if this is 25% or 35%. There's Moxy being a non-invasive tool is always going to have some discrepancy there. The fact is that a pretty large chunk of the SMO2 is not being used. So this is where it identifies it's possible here that this athlete does not have the muscular capacity to utilize all the oxygen, or vice versa if the supply is really good. And in order to maximize improvements in ice hockey in this player, we should try to increase things like muscular capillarization and mitochondrial growth and so forth. Basically just create more muscles that are going to be able to create more muscles and better the quality of those muscles to be able to consume the oxygen that's being delivered. If you go to the supply, you kind of see the same drop-off happening at a little faster rate, and it drops down near to zero, which means the athlete is obviously very well, can use the oxygen very well, can bring it almost down to zero again if this is 0 or 5% or even 10%. The majority of the available oxygen is obviously being used to produce energy, which is a good thing. We want this. The negative aspect of this, if we're going to say negative aspect, is in the example we have, it seems to work pretty good for the 30 seconds. If he had a 40-second or 50-second shift, it was a power play, he's already at the bottom. It becomes much more difficult now to play having dropped your SMO2 so low. So this type of athlete is going to be much more focusing, well, can we do something to bring more oxygen in for the athlete to then use? If you look at both the utilization and the supply graph, you see that they both actually recover SMO2 after, so in the second black line, pretty fast. As soon as they stop, those values really jump back up, which is obviously a good thing because you want recovery, you want resupply of oxygen as quickly as possible. This is where the contrast or the difference comes in when we look at the supply respiratory graph that's on the left-hand side. So if we look at this graph, we also have the drop of SMO2, very nice, and it drops all the way down to zero pretty fast. So in that sense, it's a little bit like the supply on the right-hand side. The obvious difference is that the supply on the left-hand side has a very, very long delay before SMO2 actually starts to recover again. In this case, we're talking, what is that, 10, 20, 30, 40 seconds before it even really starts to jump back up. This is obviously not a good thing to have as a hockey player, especially if you have hockey players who start double shifting. You're just not recovering, and you really need to recover the SMO2. The rationale now why we identify this as a respiratory limitation, so really specifically focusing on that, is based on theory followed by empirical findings. So we started, why does an athlete A have this huge delay and athlete B doesn't? What are the possible reasons as to why SMO2 could stay low for such a long time, this delay? And we went through a variety of different theories. And we finally landed at, well, it's possible that due to the very high intensity of the bout, where SMO2 really drops down to zero, and in the case even plateaus out at almost zero for about 10 seconds of the 30-second bout, it becomes a very non-oxidative energy production, in the sense that all the oxygen being supplied is and can be consumed. But if maximum intensity wants to be maintained, energy needs to be produced in a different way. So you start using glycolytic pathways that really then start producing a lot of additional CO2. So you have this increase in CO2 pressure, and you have to get rid of the CO2. which you have to do over your respiratory system. If you cannot get rid of the CO2, what it does, there's a term perhaps some of you have heard, it's called the hemoglobin dissociation curve. What this curve dictates is how sticky red blood cells, so hemoglobin, is to oxygen, meaning how well does oxygen bind onto hemoglobin when passing through the lungs, and how well does oxygen release when passing through the muscles. If you increase CO2, so if you start producing a lot of CO2 because of the high intensity, CO2 actually changes how that curve works. And what it does is it makes the red blood cells, the hemoglobin, much less sticky, meaning oxygen does not bind to it as well. So the advantage is when the blood is passing through the muscle, you actually get rid of, so that the oxygen really falls off of the red blood cells really easily, which is in that sense good because they can be used to produce energy. However, the other side of this is when the same blood passes through the lungs, you potentially cannot pick up oxygen as well either. So there's kind of a catch-22. So we identify that potentially what's happening is that the high pressure of CO2 is actually making the ability to release oxygen in this athlete really high and the ability to uptake oxygen low. And therefore, as long as that pressure of CO2 remains really high, they're going to have trouble trying to recover their oxygen levels, so their SMO2 values. And since we would get rid of CO2 to balance this CO2 pressure through the respiratory system, we thought, well, if someone was able to breathe more, wouldn't they be able to balance that system out faster and therefore increase recovery? So this is actually what we ended up doing. We ended up doing respiratory training, specific respiratory training with these athletes, and had a pretty effective results in increasing the recovery times of oxygenation. So just so we see some application. Now, having done these assessments, we'd identified, okay, we've got different categories of athletes who have different potential limitations. We need to now address those limitations in some kind of a training format, which goes actually directly into what I was talking about before.
Hey, Andrea, I'm going to stop you right here. We've had a couple of questions come in. So if we could take these now. We've got about 15 minutes left, so we'll take a couple of questions here, and then maybe we'll get the presentation done in about the next 8 to 10 minutes, and then we'll have a little bit of time for questions at the end. So one question here is, what are the main reasons for non-respiratory supply limitations?
Yeah, so this is a good question. The main argument that usually made is if you're able to load enough oxygen, so the problem isn't your ability to load oxygen onto the blood, so it's not at the respiratory system. The obvious next answer would be, well, it must be your ability to actually transport the oxygen to the muscles, which becomes a cardiovascular discussion. So now this is a little bit more complicated in sense. So if we now decide, okay, the problem is getting blood to the actual muscle, how do we then get more blood to the muscle? This is where THB becomes very important. So what we often see with all of the athletes who have good utilization, the hockey athletes, or supply, they actually create, during the 30-second bout, they create occlusions. So they are, due to the high muscle contraction force, they're really actually, through muscular compression, impeding blood flow to the muscles. And this is a problem. So how do we now, is just normal cardiovascular training going to be able to create, get more blood to the area if it's really just the muscles that are forcing everything shut? Now we have a couple options. One would be, if you know Romet's law, is that based on a certain percentage of maximal force production, you start really squishing the blood vessels. So one option could be, well, if we increase maximum strength, that would then decrease the percentage of the maximal strength that is required for any given intensity. Therefore, blood flow should be maintained better. That's one option that we have discussed and other people have discussed. I think I'm not always 100% sure if this is the best solution. I feel if you increase max strength, they may just end up going faster but still push the same percentage that's going to have the same effect. But at least you basically would have a performance improvement in blood flow at that given performance while at the same time increasing maximum performance. I hope that makes sense. The second option is, well, what if I can increase arterial pressure? So I can basically increase pressure to maintain blood flow by having blood pressure push through the muscular compression. That's ideas that people have also presented. Now, if that is the argument that you make, I would then say, is traditional endurance training going to help create that kind of a heart? So when we consider the type of heart that gets structured by an endurance athlete, it tends to be an increase in the size of the heart. Whereas if you look at the heart structure of a power lifter or kind of a strength athlete, you don't get that same increase in the size. You get an increase in the thickness of the walls of the heart because they're always kind of pushing against this Valsalva maneuver. And they're creating a really large blood pressure because they're forcing blood. So I don't know if I have there's two basic approaches. So apart from the increasing max strength, is one group says, no, we need to just do basic endurance training to just make the heart more capable. And another group would say, no, we need to just make this heart stronger to create more blood pressure. The success that we've generally had is more along the lines of doing more traditional kind of things. But I'm pretty open to all those ideas. I hope that kind of answers the questions. And I really hope that the idea is that experimentation, we're addressing very new type of questions that a couple years ago we never addressed, which makes people really insecure, which I think is perfectly fine to have that insecurity. We just need to be willing to try out new things, and a lot of the things, like we did with the respiratory training, is based on, okay, what is theoretically possible, and is it going to actually get the results we want? I hope that answers the question.
Yeah. Thanks for answering that, Andrew. So why don't we get back to the presentation here for about another 6 or 7 minutes, and then we'll take a few more questions at the end.
Okay. I'll try to make sure that we get to the questions. I think the questions are important. At least I hope people have questions. Next, so we had the assessments, and the second point of using this innovation is to actually apply to training. The first way to apply to training is that you apply the assessment that we did to the training programs. This kind of goes into the question that was made and into the respiratory training. So if you have someone that has a utilization limitation, that athlete or those athletes, that group of athletes, need to focus at least a portion of their training really much more on somehow trying to increase the capability to utilize oxygen. Whereas if you have these supply limitations, you really need to focus training more on that. It comes down to conditioning, coaching, experience as to what training should produce those results. So it's not always so easy picking, but you need to, at least it's an attempt to use the assessments that you made to channel individualization, rather than having an assessment that really doesn't help you at all with trying to understand how training should be structured. Now, what's important to remember is, so if you have an athlete, for example, we identified a few athletes, they have a utilization limitation. Then we get them into the weight room and they're doing squats or they're doing some kind of leg exercise. And you see, well, when they're doing these exercises, they're actually utilizing really well. and when they're skating, they're having problems doing that. This then kind of snowballs into a series of other questions. For example, technique, skating technique. Is the problem not that the muscle wouldn't be capable? It's just that from a coordination point of view, the athlete can't actually use the utilization capacity that would be around when we look at simpler kind of dry land based exercises. So this is why it's important now not just to take a single assessment and use that as some kind of absolute golden standard for how this athlete needs to do all their training. You need to, especially if you have a tool like Moxy, which is really easy to use, you need to use this in training as well to a certain extent, validate the information that you pulled out of the assessment. An assessment or any kind of test is always a one-day snapshot, and that's what's really worrisome about it. Is this going to look the same every day? And you're basing training on this, and if it doesn't look the same every day, maybe you're making wrong decisions for the athlete. But now, if you have the tool that you use to do the assessment with, and you can use it in training, you can all of a sudden pick up a whole bunch of points where you say, okay, this isn't really looking like what the assessment had initially told us. Maybe we need to do some adjustment. Maybe we need to do a reassessment. And the Moxy makes it really, really easy to do that. And therefore, it gives you as a trainer actually much more confidence in the decision that you made with the assessment. What it, however, also means is that the trainer and the conditioning coaches need to be able to understand what's going on and then make decisions for themselves, which is where we get back to the point that the physiology lab and the training needs to be much closer together. It can't just be they show up 2 times a year to do some tests and then they leave. That is, I feel, a very outdated mode of how to do kind of testing. And the other point here, before we run out of time, is not just using the Moxy as an assessment tool to guide training, but actually, like we got into, using the Moxy during training. So I think there's a lot of different things that the Moxy could be used for in training. But again, baby stepping through one thing at a time, we really felt, okay, what they wanted to use it for right away was, well, how should we do our interval training? Where are we going to get the maximum information out of the Moxy for? Is it going to help us dictate length of intervals, length of rest time? Really questions that before were unanswered, where it was just in some books someone said sprint interval is 12 seconds, or you do HIIT training 2 minutes with rest times of 30 seconds. Usually somewhat random or at least statistically based, which means if you're not in that statistical norm, it's not really going to work for you. So we really felt for the interval training, if we're baby stepping through Moxy applications, it's the first and most obvious one for the hockey players to use. So we can see in the picture here, all the athletes use slide board training to make it sport specific, and they would do intervals based on individual Moxy results. And we have the big screen up front. Each athlete has their own Moxy on, and they would do their intervals. What's important here is then that there's at least a minimum understanding of what is going on in the screen and what the goals are and how your body feels. And you need to understand when differences occur. If you expect something to happen and it doesn't happen that way, that you have the capability to question, well, why is it not happening? Should it be happening? Am I just making an assumption that's not true? Which is that really the key to individualization is to then day-to-day in training use a tool like Moxy to actually individualize. So if a training might be planned for 2 hours and it might be done after 1 hour, that's what individualization is. The individualization is in each training session. I hope that maybe there's some more questions exactly about what we're doing here. I don't know if we want to go into this much more, Roger. I can.
Well, we've got a couple of questions here. Here's one going back a little bit to the assessments. and into the training as well. Does manipulation of ventilation offset the supply respiratory limitation? This would help to prove if it really is a respiratory problem rather than continued oxygen consumption by the muscle post-exercise.
Yeah, so this is, I'm assuming what you mean, that is after the athlete finishes the bout, if the athlete willingly manipulates ventilation, that you would then see a faster recovery. So yes, we've seen that. And we usually see that, however, only with athletes that have done a solid amount of respiratory training. So what usually happens is if you get an athlete that shows a clear respiratory limitation and you get them to come sit down on the bench after a 30-second maximum effort and you tell them, okay, what we need you to do is basically hyperventilate to get rid of the CO2, they'll try and they will fail. They won't be able to do it. Which, if the limitation is the ability of the respiratory system, meaning the respiratory system is potentially fatigued from that 30-second bout, would make sense that the athlete is not capable of doing this. But if you take an athlete and you get basically the athlete to manipulate their breathing, an athlete who would actually be able to ventilate very well, but you get them to manipulate it in the other direction, you actually get this extended plateau at the bottom. So that's probably the more efficient way of proving it, because you can't get someone to ventilate well who's having trouble ventilating, but you can get someone who ventilates well to stop ventilating well. That's much more doable. And yes, then you actually see that changing.
Okay, we've got one more question here. Have you done assessments with Moxy in combination with mobile spirometry systems? Where do you see the potential benefits of combining the two?
Yeah, so I'm assuming you mean like a VO2 mobile VO2 device. So ones that we've used is there's some FitMate that are somewhat mobile. They're a little clunky. There's ones from Cortex, which are really nice, expensive ones. We've used those. I do think, so when I do assessments in the lab, I always combine ergospirometry with the Moxy data and other tools as well. Why not? I'm in a lab. It's not going to bother the athlete. The focus is whatever you do, you should just try. If you need to have a really good ergospirometry device, like a Cortex, really expensive one, if you're going to do it on the ice. And you could do it, a lot of athletes complain about the mask and they feel they can't really get the performance done that they want. What you're just going to get out of it is more valuable information about the respiratory system. And what's nice about that, and the reason I do it when I do lab tests, is if you make an assumption on the Moxy data, for example, changes in CO2 and changes in the hemoglobin dissociation curve, and that should be seconded by the ergospirometry data. If it's not, then you need to start thinking about what decisions you're making and why are those pieces not coming together as you had assumed, and which means you made a mistake. As long as the data, the machines are working properly, then the mistake is in the theory, because the theory needs to fit the data and not the data fitting the theory. So yes, I do think it's helpful. I don't think it's feasible with a hockey team to get it done, because they tend to be pretty expensive. I know the Cortex is pretty expensive. So if you want to get a whole team tested like that, you need to find a hockey team that's willing to do that, which I haven't found. And the mask can be annoying. So I've used mobile ones. Yeah, that's the second point. But generally, obviously, more information, the better, as long as you can somehow get through the data to come up with something that all fits together. That would be a second problem. It's wheeling through the data and not just having tons of measurements that look nice, but again, the goal is performance gains and not physiology.
All right, great. With that, our time is up here. So thanks everyone for listening, and thank you, Andrew, for presenting. We will get this posted on our website. We'll get a recording posted on the website, and then we'll also have a link to our forum. So if there's any other questions that you would like to ask Andrew, just find the link on our website and go on the forum, and we can continue the discussion there. So thank you again, Andrew.
Thanks a lot, Roger.